Good day, good evening, everyone. Today, I will be presenting an overview of file organization in database systems. This topic is fundamental to understanding how data is stored, accessed, and managed efficiently. Let's dive into the key concepts starting with basics. As we already defined, a database is essentially a collection of files, and each file is a sequence of records, and each record is a sequence of fields. So one common approach to organizing files assumes that records are in fixed size, that each file contains records of a single type only, and that different files are used to store different relations. This sets the foundation for how data is structured. So here we explore fixed length records. A simple approach is to store each record I starting at byte n times I minus 1, which makes accessing records straightforward. However, a downside is that records might span across blocks. To address this issue, we can modify the approach to ensure records does not cross block boundaries. So we can see here in this table, this is a fixed length records with IDs. You can see IDs here, names, departments, and salary for instructor table. Another strategy is to avoid moving records during deletion. Instead, link free records into a free list, which we will discuss further. So here we can see one example. For example, here we can see here the record number 3 is Einstein for physics department, right? So we have removed this, so 3 is not here anymore, and instead we have moved up each record once, right? So as you can see here, we have many movements, right? When one record is deleted, all the next record must be moved up. So this is called as compact, right? So we shift up to fill up the gap and we maintain a contiguous structure. So this approach, we call it as compacting. This ensures no empty space remain, but it requires moving all subsequent records. This is computationally expensive. Alternatively, instead of compacting, it means we move up all the records. In here, you can see we have 11 records came for electrical engineering. We move this one instead of record number 3, right? So you can see here record 11 from the end moved here. This reduces the amount of data movement compared to compacting, as only one record is relocated. So it's a trade-off between maintaining order and minimizing overhead. Now let's look at free lists, a more efficient way to handle deletions. Instead of moving records, we store the address of the first deleted record in the header file. That record then points to the next deleted record, and it creates a linked list of free spaces. This method is more space efficient as it reuses deleted slots without reorganizing the entire file. So once one record has been deleted, we store the address of the first deleted record in the header file. Moving on to variable length records, we see they offer more flexibility. There are three main approaches that you can see here. First one is storing multiple record type in one file. Second one is allowing fields like strings to vary in length and supporting repeating fields, which was common in older systems. So in here, attributes are stored sequentially and null values are tracked efficiently using a bitmap. For example, here you can see we have some information here stored, and this 0000 indicates a null bitmap. For variable length records, the slotted page structure is a key technique. The header of each block tracks the number of records, the end of free space, and the location and size of each record. This layout, as you can see in this image, allows dynamic allocation of space and make it ideal for records of varying lengths. So here we can see 4 ways to organize records in a file. The first one is heap. The heap method places records wherever space is available. Simple but unordered. The second one is sequential. Sequential organizations sorts records by a search key for efficient retrieval. Hashing uses a function to map records to specific blocks based on an attribute. Finally, we have multi-table clustering for organizations. This multi-table organization groups related records on the same block in order to reduce input and output operations. Here is an example of sequential file organizations. As you can see, records are ordered by a search key, and that one is ID. So as you can see, the table lists instructions from ID 10101 to 98345 in ascending order, making it easy to perform range queries or binary search. In sequential files, managing update is critical. For deletion, we use pointer chains to make free spaces without disrupting order. For insertions, we find the correct position based on the search key, but if there is no space, we use an outflow block to store the new record temporarily. This maintains the sequential structure efficiently. So here we can see multi-table clustering. This multi-table clustering combines related records from different relations into one file. Here we have a department table, and in department table we have department name, building, and budget. And also we have instructor like ID, name, department name, and salary. We have 2 tables separately, but in the clustered version here, records from computer science and physics are grouped with their instructions on the same block. This reduces input and output when querying related data like all instructors in a department. Next, we have data dictionary storage. The data dictionary is a critical component that stores metadata. Metadata is simply data about data. This dictionary includes details like relation name, attribute types, view definition, and integrity constraints. Also, this dictionary may track user information, statistics like tuple count, and physical details such as whether a relation is stored sequentially or hashed and its location on disk, and many other information can be stored in a dictionary. System metadata builds on the dictionary concept. This system metadata, it's stored as a relational structure on disk, and they use some specialized in-memory data structure for fast access. So this system metadata includes relational metadata like names and storage details, index metadata for indexing strategies, view definitions, attribute specifics, and user credential, all essential for managing the database system. So here we can see we have relation metadata, relation name, number of attributes, storage organization, location, and the rest that you can see for index, for view, for user, for attribute. Finally, we touch on storage access. First, we have buffer. The buffer is a portion of main memory, and it is used to hold copies of disk blocks. Why we use this one? For speeding up data retrieval. And then we have buffer manager. It's a key subsystem, and it is used to allocate this space efficiently in order to optimize performance between disk and memory. So, in conclusion, file organization is the backbone of efficient data management in databases. We have fixed length records that they provide simplicity and predictability, while variable length records offer more flexibility for diverse data. We also explored methods like sequential, heap, hashing, and clustering. Then we learned that metadata in data dictionary and storage access via buffers. So learning this concept is essential for building robust, scalable database systems. Thank you for your attention, and please feel free to reach out with any questions, comments, or concerns either via email or by leaving a comment below this video. Thank you.